This is Kevin Cole at the University of Nebraska. The topic is Database of Exact Solutions. This talk was originally given at the Inverse Problem Symposium in East Lansing, Michigan in June 2018. Let me look at an outline. I will motivate the talk. I'll say some things about the Exact Analytical Conduction Toolbox, EXACT for short. I'll review some heat diffusion basics, including the Green's function and our numbering system for heat conduction. I'll give a couple examples of solutions from the EXACT database, and I'll summarize. So why a database of exact solutions? Even though we live in the computer age, we still need exact solutions. We still need analytical work as benchmarks for fully numeric work. In the inverse world, we need direct solvers to get the solution in the iterative method. And if you have a real-time process control situation, you need a solver that's fast. And many times exact solutions have that. And I am interested in analytical solutions as building blocks for semi-analytical methods, for combinations of theory and numerics. If you're looking for exact solutions, the usual places are books and journals. But there's no consistent organization. There's no index. If you send a graduate student to go find things and the solution is a little bit older, 1990 or earlier, it's not going to be indexed in an electronic database. Now, many journals are getting better at indexing their old content. And then even if you find a solution, you have to do some work before you can get numbers out of it. It has to be interpreted or translated. There might be eigenvalues to be found. You might have to evaluate special functions. There might be integrals that you have to evaluate, and so on. So when I think about exact analytical solutions, it's kind of like that furniture you buy that comes packed flat, and you have to build it. You have to put it together. There's some assembly required. So you open the instructions, and there's this cartoon of which tools that you need. And for the computer world, the exact analytical solution world, you might need a programming language. You might need to evaluate special functions. You might have to find roots. If there's a series, you have to worry about convergence and round-off error. If there are integrals, you've got to find a tool to do the quadrature. You've got to worry about convergence. So the issue is, in the 21st century, most students and working engineers are not confident in doing these steps to make good use of exact analytical solutions. So we've constructed this thing we call the Exact Analytical Conduction Toolbox, and we have systematized some of the steps needed to apply analytic solutions, and our focus is heat conduction. You've got to find a solution, you've got to understand it, you've got to check it and get numbers. Well, to find it, we've got a number system for heat conduction, and we've assembled a database of many, many exact solutions. The URL is exact.unl.edu. You've got to understand a solution. Well, we include pitfalls to avoid when getting numerical values. We include our algorithms and computer code for each of the solutions on the exact database. You've got to take a solution, you've got to check it before you get numbers. Well, we have something we call intrinsic verification, and we show how the solution is correct. We check the solution against itself or against some other close-by solutions. We've included tables of high-precision numbers and some graphs. So if you have a checking situation, you might be able to get results right away. You might get what you need from the tables that we've got. If you don't like our numbers, use the code and compute some others. So exact.unl.edu is the website. It was launched in 2013. There's 130 solutions there now. Each of these is a PDF document describing it. You can search for these solutions by keyword, by geometry, by our numbering system. Each of the solution documents includes a problem statement, expressions for the temperature, discussion of verification, especially intrinsic verification, brief tables of precise values, some plots, and some code. The goal here is to encapsulate the knowledge and experience from the people that have assembled this thing and make it widely available. Some of the people working on this project are retired, and the legacy of storing their expertise has been very important. This is applied to heat conduction problems, but this is a model for other physical phenomena because the PDE's partial differential equations describe many physical effects, acoustics, electrostatics, fluid flow, and so on. All right, so I've said a few things about the exact analytical conduction toolbox. Let me move on and look at some diffusion basics. So here's a definition of heat conduction or heat diffusion. It's a relationship between a temperature distribution and the rate of heat flow. And applications include thermal sensors, property measurements, thermal control. So Fourier's law says that the heat flow is minus the conductivity times the flow area times the spatial derivative of temperature. So here's some units. Q is watts, T is kelvins, area is meters squared, and thermal conductivity is watts per meters per Kelvin. Now, the one-dimensional heat equation is parabolic. It's second derivative in space and first derivative in time. And the other parameter I need here is alpha, the diffusivity in meters squared per second. If the material properties are not functions of temperature, then this is a linear equation, and we can use superposition. If we've got two solutions, we can create new solutions by linear combinations. All right, so a couple basic ideas there. All right, to solve that heat equation, we need two boundary conditions and one initial condition. Again, I'm talking about one-dimensional for the moment. The heat equation plus these conditions is called the boundary value problem, and the solution is unique. Boundary conditions, let me number them. Type 1 is temperature specified. Type 2 is slope of temperature specified. Type 3 is sometimes called a convection condition. It's a combination of specified value and specified slope. And then we also use type 0 to represent a situation where there's no physical boundary. That might be a boundary far away, semi-infinite or infinite case, or that might be the center of a cylinder or sphere. All right, we use a heat conduction number to keep track of things. It's a specific and concise identifier for a heat conduction solution. We use it to uniquely characterize and identify solutions, and it helps us store and retrieve solutions. It also provides some insight because the number tells us what problems are closely related. I'm going to say a couple things about the number system here. It's also outlined at exact.unl.edu, and it's fully described in our recent book on heat conduction called Heat Conduction Using Green's Functions. All right, so here's an example of a number system. Here's a one-dimensional problem. It's got x coordinate here, and the number is x32b10t1. Which situation are we talking about here? Let's parse this thing into pieces and talk about it. So the first bit I want to talk about is x32, and x says, okay, we got an x coordinate system here, so that tells me it's a slab body. The 3.2 says something about the types of boundary conditions present. So type 3 says, number 3 says there's a convection condition at x equals 0, so that's this boundary here. And the 2 says there's a heat flux boundary type at x equals L. So over here is a slope specified. That takes care of the first three numbers. The next bit is B10. The B says boundary information is coming. The 10 says that there's a constant value at the first boundary. So here is a constant value of type 3. So the constant would be the fluid temperature and the heat transfer coefficient are specified at this boundary. The 0 says the other boundary is homogeneous. A homogeneous boundary of type 2 is insulated. The last part of the number is the T1, and the T says initial condition information is coming. So that telegraphs that this is a transient problem. The number 1 says that this is a uniform value. So a uniform initial condition here. So that's a number for a slab condition. Let me say a few things about the Green's function, and I want to focus on, for a moment, an x21 case. So x21 says flux specified, and at this side, temperature specified. Here's the one-dimensional heat equation. I've got an initial condition, that's a function capital F of x, a position, function of position. And then I've got boundary conditions at x equals 0 and x equals L. This one is a heat flux history, and this one is a temperature history. So this problem has quite a large family of solutions depending on the function I choose for capital F, little q, and little f. Well, using the Green's function, if I know the Green's function for this geometry, then any temperature solution for this geometry can be written down in an integral form with the Green's function solution equation. So let me write down the formal solution to this family. The Green's function solution says the temperature is the sum of three integrals. There's one for the heat flux at the boundary, there's one for the specified temperature at the boundary, and there's one for the initial condition. So my three functions here appear. Here is little q, it's multiplied by the Green's function, evaluated at the appropriate boundary, x prime equals 0. The other condition here is taken care of its contribution by this integral. So here's the time history of the boundary temperature. It's multiplied, it happens to be the derivative of the Green's function, evaluated at that boundary and integrated over time. And then finally, the effect of the initial condition comes in. I multiply the initial condition times the Green's function, now evaluated at time 0 and integrated over space. So it's this kind of approach. This is a superposition effect. Green's functions are building blocks for constructing a wide variety of solutions. All right, what is the Green's function? It's a simple solution to the heat equation. It can be superposed to construct useful solutions. It's the temperature response at an observation point, x and t, due to an impulse of heat at a heating point, x prime and t prime. So the one-dimensional Green's function depends on four variables. It's the heating, the observation point, and the heating point. The Green's function depends on the body geometry. In this case, it's a slab wall, and on the type of boundary conditions present. So x21 describes the Green's function. Because I need to have homogeneous boundary conditions of type 2, matching the problem I want to solve, and another homogeneous boundary condition of type 1 at x equals L, again matching the problem I want to solve. So the boundary and initial conditions are homogeneous. The heat source is dropped in by a delta function at location x prime and t prime. All right, so that's a brief look at what Green's functions are. I want to talk about the shape of the x21 Green's function. I've got a movie I'm going to show in a moment. This slide is static, but I'm dropping in the heat for the same Green's function here at point 1, and then I've got a picture of the same Green's function, but now the heat's being dropped in at point 9. Let me see if I can find that movie here. All right, so here's the two Green's functions. This is the x21 Green's function, so this boundary here is a type 2 boundary, so it's a slope condition here. So that's always a 0 slope. When I drop the heat into point 9, though, the x equals L boundary is a type 1 boundary, and homogeneous means that the temperature is clamped to 0. So this heat flowing out at this boundary because the temperature is clamped to 0. And at late time, you can see that this function is higher than this one because of the heat that's being drained out at that point. All right, let's go back to the slideshow here, and I'll continue on to give a couple of examples from the exact database. So here's a solution that's in the exact database. The number is x21 B10T0. So that's the one-dimensional heat equation in a slab between 0 and L. I've got a uniform or constant flux at this boundary, and everything else is homogeneous. So there's one driving term, it's a constant flux. So the Green's function solution has one integral. I take that constant flux, multiply it by the Green's function, evaluated at x prime equals 0, integrate over time. Here's the Green's function. It comes from a Fourier series approach. The integral I need is on time. It lands on the exponential on time inside the Green's function. So here's an expression for the temperature in this body over time. Let's go on to the next page. So here's a restatement of that expression from the last page. Here's some plots. At early time, the heat flows in from this boundary, and then most of the temperature is 0. At later time, the heat flows in and begins to fill the body. At late time, the temperature approaches a straight line. This expression that gives these plots has two terms, a steady term here, this 1 multiplied by the cosine and divided by beta here, and the transient part, the exponential. It turns out that the steady part converges very slowly. It goes like the sum of -1 to the m over beta, and beta goes like this, proportional to m. You can find the steady solution independently by integrating the steady equation twice. It's a straight line. If I substitute this into the above expression, I get this expression. This is the recommended form, the solution for crunching numbers, because it converges well. So this is a very simple example, but this kind of substitution, this kind of information on what's the form of the equation that behaves well, is the key information that we put in the exact database. All right, here's another example of a solution that's in the exact database. This is a steady example. The number is x11b00, y23b10. So the fact that there's an x and a y says that this is a two-dimensional problem. And the fact that there's no t designator, it's a steady problem. So here's the heat equation in 2 dimensions, steady. It's Laplace's equation. The boundaries are there's 2 type 1 boundaries. So that along the x coordinate, I've got a type 1 here, type 1 there. It's homogeneous, so the temperature is 0 there. In the y direction, I've got y23, so that's a type 2 condition here, type 3 condition here. B10 says that I've got a specified constant flux at this boundary, and I've got a homogeneous convection or heat loss to fluid temperature 0 over here. All right, I've got 2 expressions for the solution. If L over W, that's the coordinate, that's the aspect ratio. L is the distance, the length in the x direction, and W is the length in the y direction. If L over W is large, here's the recommended form of the solution. It's a single sum, and it has eigenfunctions that are cosines in the y direction. We've got an alternate solution. If L over W is small, the recommended solution is an infinite sum of eigenfunctions in the x direction. And you might say, wait a minute, a boundary value problem has a unique solution. How is it that you've got 2 solutions? Well, this is the same solution, but these are different expansions of the same solution. And they have different convergence behaviors. So here's some temperature values computed from these 2 functions, from those 2 expressions, and they agree to 10 decimal places. Now, the underlined part is where they don't agree. And depending on where you are in the body, and near the boundary is one of these behaves badly. This particular set of tables is for L over W is 0.05. So this is a small value of the L over W ratio. And it turns out that one of these expressions converges quickly and one does not. And it's very terrible near the boundary. Well, if you've got 2 independent expressions, the checking is very strong. I know that these numbers are correct because they agree to 10 digits. One of the applications is checking the fully numeric code. All right, let me summarize. I've been talking about exact solutions in heat conduction, and they're important, even in the 21st century, for benchmarking of fully numeric work, as direct solvers for inverse problems, and as building blocks for semi-analytical methods. We've got a database that we've been talking about, exact.unl.edu, that contains heat conduction solutions organized by a numbering system with added tables of values, with plots, with algorithms, and computer code if you want to get your own numbers. Ongoing work, we're developing new cases with generalized boundary conditions, and codes from 59 of the cases that exist on exact have been taken and put into the MATLAB file exchange as subroutines. My student Miracle Kanu Asegbu has done this work for me. There's 59 cases there, so it's another way to have access to the information in the exact database. All right, I want to acknowledge funding from the National Science Foundation, and here is some the members of the exact team. Don Amos and Jim Beck are retired. Paul Crittenden, a former student at Jacksonville University. Filippo Damonti in L'Aquila, Italy. Haji Sheikh at the University of Texas, Arlington. Robert McMasters at Virginia Military Institute, and Keith Woodbury, University of Alabama. Thank you.